In this lesson, we'll be looking at exponential functions. Our objectives will be to introduce exponential functions, to examine graphs of exponential functions, to determine if a data set is exponential, and to write an exponential function to model data. Let's begin with a discussion of functions, and let me remind you of some things you already know. First of all, we've already talked about linear functions. We've talked about quadratic functions, and now we'll be talking about exponential functions. Linear functions are those that can be written in the form f of x is equal to mx plus b. Can you remember what the form is for a quadratic function? ax squared plus bx plus c. And now let me introduce you to the standard form of an exponential function. F of x is equal to c times a to the x power. Let me give you an example of a linear function. F of x is equal to 2x minus 4, where remember 2 is the slope and 0, negative 4 is the y-intercept. Let me give you an example of a quadratic function. 2x squared plus 4x minus 5. You know that you could tell me this quadratic function opens up because a is positive. You could calculate an axis of symmetry and a vertex for me. I also want to remind you that a quadratic function can look much more simple than this. It could just be x squared, and it's still quadratic. So now let's look at an example of an exponential function. F of x is equal to 4 times 1/2 raised to the x power, where c is equal to 4 and a is equal to 1/2. A much simpler exponential function could look like this. F of x is equal to 2 to the x power. In this case, a is 2 and c is 1. You don't see it written there. I also need to make sure that you understand, for this to be an exponential function, a and c have to both be greater than 0, and a cannot be a 1. If a is a 1 and you raise it to some power, you just get a 1, and you'd end up with a linear function again. But it is important that a and c are both greater than 0. You know what graphs of linear functions look like. They're straight lines. And you know what graphs of quadratic functions look like. They're parabolas. So let's look at graphs of exponential functions. Let's start with the two exponential functions we've just looked at. F of x is equal to 4 times 1/2 to the x power. If I entered that in my calculator, 4 times 1/2 raised to the x power, and I graphed it, I would see a picture that looks like this. Not like anything we've graphed before. It definitely doesn't look linear, and it definitely doesn't look like a parabola. Let's look at the other one. F of x is equal to 2 to the x power. If I graph that, it looks like this. Now, I hope you begin to see some similarities. When we graphed lines, they didn't all look exactly the same, but they were all straight lines. When we graphed parabolas, they could open up or they could open down, but they still had that basic shape to them. Well, it turns out that this is the basic shape of an exponential function. There are some things you need to be aware of. I realize when you look at the graph on your calculator, it kind of looks like it ends right out here, but you need to understand, it doesn't. It just continually gets closer and closer and closer to that x-axis without ever touching it. Your calculator can't really do a good job of showing you that, so you need to be aware that that's what happens. The domain then of an exponential function goes from negative infinity. This part continues to go to the left to negative infinity, and this part will continue to go to the right. By the way, this one also does the same thing, it just does it in reverse. This part will go infinitely far to the left to negative infinity, and this part will go slower, but it will go infinitely far to the right. So they both have a domain of negative infinity to positive infinity, as do all exponential functions. Let's talk about the range of exponential functions. Remember, range talks about the y values. Well, this time, look at the y value. It never drops below the x-axis. So the range goes from 0 to positive infinity on both of these problems. The other thing I need you to notice is that there will never be an x-intercept. You know how when we were graphing quadratics, we told you that if you wanted to solve, you could do that by looking for the x-intercepts? Well, there are no x-intercepts on exponential functions. They never cross the x-axis. So an x-intercept is not an interest for us in this type of function. One thing that is of interest to us, though, is that the y-intercept is always 0, c, meaning if I could identify the y-intercept, the place where the exponential crosses the y-axis, I would know what c is. And let me remind you, that's the number right out here at the first. So look at this. Notice that this one has a c of 4, and its y-intercept is 4. What did we say the c was on this one? You don't see it written there, but it's an understood 1. Well, look where this crosses the y-axis. So it turns out that we can get some information by looking at that graph. By the way, since we've just been talking about this, I'm telling you the function is 1 to 1. Can you tell me why? Because it passes both the vertical and the horizontal line test. And if it is 1 to 1, then it's guaranteed to have an inverse. And that's going to really play a role for us in the section we'll do next involving logarithms. Now let's look at some data and see if we can determine whether or not it is exponential. I'll give you two tables of data and we'll look at both of them. In the first one, I want you to notice that we see the x values increase by 1 each time. Notice that the y's increase by how much each time? Well, each time there's an increase of 3, while there's an increase of 1 right here. That tells me that this data is linear. By the way, I know that because I could actually calculate a slope. Y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. And it's pretty obvious the slopes are the same. It turns out that the slope is 3 over 1, the difference in the y's over the difference in the x's. And that's consistently 3 over 1, 3 over 1, 3 over 1. So that's linear data. And by the way, right here, you know what the y-intercept is. It's 0, 2, which means if you wanted to, you could actually write the linear equation. Y is equal to the slope, 3x, plus the y-intercept, in this case a positive 2. Let's look at our next data set now and see if we can determine whether or not it is linear or something else. Notice this time that the x's still increase by 1. But what do the y values increase by? Well, it turns out that this data is exponential because the y values increase by a factor of 3. Let me explain what I mean by that. 1 times 3 will get you this piece. 3 times 3 will get you this piece. 9 times 3 will get you this piece. So it increases each time by a factor of 3. Over here, it increased by adding 3 every time. For exponential data, we're looking for a factor that it's multiplied by. In this case, it is a 3. I also want you to notice that once again, I know the y-intercept. It is 0, 1. And we said that y-intercept was important in exponentials as well. Remember, we said the y-intercept would be the number that appears right here. It is c, and so I know this goes right here. And I found it just by looking at the chart and noticing where is x equal to 0, because that's what a y-intercept is. It turns out that whatever factor this data increases by is what a is, right there. So an equation for this exponential data is y is equal to 1 times 3 raised to the x power. And the thing that's unique about exponentials is this. We still have an x, it's a variable, but this time you'll notice it's an exponent. We've never had that before. In linear equations, it's right there. In quadratics, remember, it was ax squared plus bx plus c. We had exponents, but they weren't variables. They were just a number. But in exponentials, we notice that that x is the exponent. Now I want to talk to you about modeling exponential data, and I want to give you a very simple way to do this. First of all, we can notice that this increases by 1 each time here, and on the bottom, it's pretty easy to pick up on this one quickly. What is the factor here? Each time it gets multiplied by 3, I'm guessing. Why don't you check? Is 18 times 3 54? If it is, then we truly do have exponential data again. And you could stop right now and write the equation for that. Y is equal to, what is the y-intercept? You get it from right there. So it would be 2 times the factor that it increases by each time is 3 raised to the x power. But I want to show you another way to do this, just in case that bothers some of you. We can do this using the calculator as well. Remember how you did a linear regression? And we've also done quadratic regressions? Well, it turns out we can do exponential regressions also. So another way to find this right here would be to let your calculator find an exponential regression. You would enter the data in your calculator like I have done right here. Remember, that's stat, edit, and then enter the x's as L1 and the y's as L2. Once that's done, you go back to stat, choose calc this time, and it won't show up on your screen immediately. You'll have to scroll down further, but when you get down to 0, you'll see exponential regression. Well, that's the one we're looking for. So if you enter 0, you'll get y is equal to a times b raised to the x power, and it tells you that a is 2 and b is 3. Now I want to give you a word of caution. In our formula it says y is equal to ca to the x. Please don't get this confused. The number they give you right here is the number that goes at the beginning. It's what we call c. The number they give you here they call b, and it's what we call a right here. But it's not hard to remember that because they tell you right on the screen where each number goes. But I just want to make sure that you don't get confused thinking this is what we call a. It's not. But plucking those numbers from there and writing your exponential equation is not a big deal. So it is indeed f of x is equal to 2 times 3 raised to the x power. What I want to do now is I want to take some more data and see if we can write exponential functions from that data. Our instructions are to find c and a so that f of x is equal to c times a to the x power satisfies the given conditions. And the conditions we're looking for are f of 0 is equal to 10 and f of 1 is equal to 30. Let's just pause for a minute and make sure you understand what that means. One of the ordered pairs that you know is 0, 10. The other ordered pair that you know is 1, 30. You could stop right there, go to your calculator, enter those two ordered pairs of numbers, and ask it to calculate an exponential regression, and be finished with this problem. I do want to make sure you understand, though, you still have the option of doing this manually. We know that this is your y-intercept, so I already know that this is y is equal to 10 times, well, what factor does it increase by? To go from 0 to 1, I go from 10 to 30. What is the factor right there? Well, it's 3 to the x power. So if I put it in my calculator, it would look like this. And when I do the exponential regression, I get this. When I plug those numbers in, I get f of x is equal to 10 times 3 to the x power. So I can do it by examining the data, or I can do it using my calculator. Either way. Let's look at another one. Use the graph of y is equal to c times a to the x to determine c and a. Well, look at the graph this time and tell me, if I don't have the equation written down, but I want to know what c and a are, can you tell me what c is fairly quickly? Remember, c is your y-intercept, so I can already tell you that c is equal to 2. Now, it may take us a little more effort to figure out what a is, but let me remind you. 0, 2 is one location I know on that graph. What is the other one that I know? When x is 1, what is y? And you may need to count it. 1, 2, 3, 4, 5, 6, 7, 8. Well, let me ask you, what is the factor that takes me from here to here? Well, it's a 4. So I know that a is equal to 4. What would I need to multiply 2 by to get that 8? Well, it's just a 4. So I know that c is equal to 2 and a is equal to 4. Let's also look at how we could do that on our calculator. I would go to Stat and Edit and enter those 2 points. I would then ask my calculator to do an exponential regression, and it comes back with that same 2 and 4. So y is equal to 2 times 4 raised to the x power. And to complete the task we were given, we need to determine c and a, so c is equal to 2 and a is equal to 4. So far, exponentials aren't so bad. It may get a little hairier before we're done, but not so bad now. Let me leave you with my thought for the day. Be true to your work, your word, and your friend. Have a great rest of the day, and I'll see you again soon. Bye-bye.